Okay, so we're going to learn about polynomials. We're going to learn how to graph them. And a few of these polynomials you've learned about already, like the linear function. Chapter 1 we learned about the quadratic function. But what about bigger polynomials? Well, we're going to look at those today. We're going to learn how to evaluate them and so on and so forth. Pretty easy stuff. It's not terribly hard. But let's get going. So, lesson 2.2. So, those of you who are taking notes with Cornell Notes, you can write down the objective and the essential question. Students will be able to graph polynomials. That's our goal today, and naturally, we would like to know, how do you graph? So, let you write that down if you like. Okay, so polynomials. The main thing is that polynomials are made up of a bunch of terms. Poly means many, and so what is it made up of? Many monomials. Monomials is a single term. But there are a couple other things you need to realize, is that when we have polynomials, the exponents are always whole numbers. So we won't have any fractional exponents. For example, we won't have like y is equal to, say x to the 1/2 power. This would not be a polynomial because of this half power here. It's always going to be whole numbers up there. Like we've had polynomials already. We've had a quadratic, for example, x squared plus 2x plus 5, for example. There's our quadratic. And so there's certain things we want to know about polynomials. Certain new words that we're going to talk about. One of them is degree. I think that's here somewhere. Hang on. So n is the degree of the polynomial, and then we have a couple other ideas. So let's talk about the degree, for example. When we write things in standard form, what we do is we write the highest exponent term first, and then the next highest exponent, and then the next highest exponent, and the next highest. So when it came to quadratics that we just had, we would write the x squared term first, and then we'd write the next highest exponent term, and then finally once we get all the x's done, then we finally write the constant term, if there is one. So that's how we would write a quadratic. And so
this car broke down.
Thank you. Bye, Freddie. Now, so a polynomial in standard form just means that you write the highest degree term first, the next highest, so on and so forth. Now, by degree, we're going to say the degree of the polynomial is always the biggest guy, the biggest exponent here. So, for example, the degree for this polynomial would be equal to 2. And so, if you have another polynomial that looks like this, just make one up here real quick. The degree on this one would be degree 4. It's the exponent that is the biggest. And now notice the degree here would be, the degree of this monomial is 1. The degree of this one is 4. The degree of this one, you can think of this as having an x to the 0 on there, because we found out yesterday, what's x to the 0? 1. So this is the same thing as 17 times 1 here. And so the degree of this monomial, we'd say, is 0. We'd say 0. So each monomial has a degree, but the degree of the polynomial is the one that's the biggest of the whole group. Does that make sense? So, and once we know something about the degree, then we know something about how many turns it takes. And so, I mean, we learned about parabolas that they could have one turn. Does that make sense? And that's with degree equal to 2. If the degree is 3, for example, then there could be at most 2 turns. If the degree is 4, then you might have 3 turns. And so the degree tells us something about the polynomial, among other things. And we're going to learn some of those things in this chapter. Well, so there's some basics on a polynomial. And primarily what we're going to do is try to graph them, and we're going to try to evaluate them at certain numbers. So let's continue. This table here shows some of the common polynomials that we've seen so far. The first 3 up here we've seen before. We've seen these 3 already. This is your constant function, like when f of x is equal to 3 or negative 3. That's our function that looks like, well, you go down here 1, 2, 3, and we'd have a line that comes through like this, and that would be our constant function. That one. This one right here is a linear function, and you've seen a whole bunch of linear functions. This line, for example, has a y-intercept of negative 4, and if we were to graph that real quick, it has a slope of 2 to 1, so it would go up 2 and over 1, and have another point here, up 2 and over 1, and so that would be some line that comes through like this. So there's our, what's the degree on this one, for example? In this case, the degree here is 1, so the degree is 1. Okay, what's the degree on this one? We would say degree is 0. The degree is equal to 0, because you could put in an x to the 0 on there, and then the exponent value there is 0. And again, what's x to the 0? X to the 0 is equal to 1. So this is the same thing as multiplying by 1. What's the degree here? Oh, it's 2. Does that make sense? Now, if I were to graph one of these, the parabola, like I said, it's just a curve with 1 turn in it. It has a maximum. Sometimes parabolas have a minimum. Okay? So that's degree 2. Okay? Okay, that's equal to degree 2. This is a cubic. So the special name for these guys are called cubics, because its degree is 3. And then if the degree is 4, we say it's quartic. Quartic. What do you think degree 5 is? Wow, something. After a while, we start giving generic names. It's just, I don't know. You could probably look. What is it? A quintet? No, I don't know. Quartic? Quadratic? I don't know. To be quite honest, I don't know what the 5th power one is called, but I would know that there's an x to the 5th over here, in there somewhere. Does that sort of make sense? Now, by standard form, we always write the highest degree x first, the next highest degree x, and then the next highest, until finally we get to the constant term. So you're going to just have a few problems where they just say write the polynomial in standard form. All that means is put them in the correct order. That's it. Any questions? Pretty easy so far, right? Even a first grader can handle this, I think. All right, maybe a smart first grader. All right, so now we're going to learn how to evaluate, and I'm going to show you 2 methods on how to evaluate. One's a long way, I think, and one's a little bit shorter way. You'd be surprised. So the first way we're going to show you is direct substitution. Okay, direct substitution. What that means is you plug the number in. You take this x and you plug it in right here. Oh, by the way, you plug it in right here as well. And you plug it in right here, you plug it in right here. You do all the little calculations and see what it equals. So when we're evaluating this, what we'd say is that, well, f of 3, and what that means, f at the value of x equal to 3 is equal to 2 times 3 to the 4th power minus 5 times 3 to the cube power, or the 3rd power, minus 4 times 3 plus 8. Okay? So this isn't terribly hard, but it's easy to make a mistake. My friends, when I give you a test problem like this on the test, please don't miss it.
Wow.
It's just too easy. Come on, all you do is plug the number in, see what you get. Well, 3 times 3 is 9, and times 3 again is 27, times 3 one more time is 81. So this is 2 times 81, minus 5 times 3 cubed here is 27. And then this part I could calculate, that's 12, and then plus 8. Well, so now I'm just going to go maybe one more step here, and I'm going to use my calculator now to help me out. 2 times 81, of course, is, well, 2 times 80, what? 162. And then, so this is 162 minus 5 times 27. What's 5 times 27? 135. And then I subtract 12, and then I add 8. And I think we can finally say f of 3 is equal to, well, let's see here. 162 minus 135 minus 12 plus 8. I get 23. Bam. Everybody good with that? Now, what we just found out, and this is where graphing gets annoying. When you're doing polynomials, graphing is annoying. What we basically found out is that when x is equal to 3, here's 3. When x is equal to 3, the y value, remember this is basically y at the value of 3. What we found out is that the y value is 23. So if we were going up by 4s, 4, 8, 12, 16, 20, and then the next one would be 24, we would have a coordinate right about there. And so this polynomial, this quartic, it's kind of annoying to graph, because what we've done in the past is we create a whole bunch of values. Like, remember what we do? We do x and we do y here. Well, what we're going to have to do is plug in a whole bunch of points. And what we just did was found out the point when x is equal to, say, 3. Now what we're going to probably want to do is like -2, -1, 0, +1. In order to graph one of these polynomials, we have to plug in several points.
Does that cheat code still work? How if you have the same number is like you have -1, whatever you get for that is going to be the same thing as +1?
There's a parabolas, we often had a line of symmetry, but polynomials probably will not have a line of symmetry. And not always, but probably you can't assume that it will. So as you might imagine, if we have to plug in 6 or 7 of these points, and you're going, dang, to do one stupid little graph, it takes 15 minutes to get all this information here. It's kind of annoying. So thank goodness we discovered a little bit faster way to do this. So I'm going to show you a little bit faster way to do that. And we're going to call this synthetic division. Well, the method is synthetic division. We use it for synthetic division also. So I want to warn you, what I'm going to show you right now, please learn it. Because we will learn this, we will use this idea multiple times the rest of this chapter. Does that make sense? And you want to be pretty good at doing this, pretty fast. So, no, you need to learn it too, Noel. Okay, so we have the same function we did before. And we remember, we just did this. We found out that f of 3 is supposed to be equal to 23. Right? We just did that a few moments ago. Alright? Now I'm going to demonstrate to you something here. And I have to show you all the little bits and pieces on how this works. But synthetic division. Alright, well here's how it works. We make a little half box here. Start off by making... Now by the way, you might want to copy this on your notes somewhere. Alright. And we put the number 3 here. Okay? We start off by putting that number here inside this little half box thing. And then right along the top here, we put all these coefficients. However, there's one little thing you have to watch out for. Do you notice the degree here is 4? You see that? And then the next term is a 3. Anytime there's a missing term in the polynomial, you have to put a 0. Okay, so here's what I do. For this one, I write down a 2, because that one's there. And this one, I put a -5, because that one, the third power term is there. But notice there's like a 0. If you wanted to, you could put a 0x². There's no x² term in here. You see? So when you're doing synthetic division or synthetic substitution, you have to put in zeros if there's missing terms. So right about here, I'm going to put a 0. And then I'm going to put a -4 from this one. And then I'm going to put an 8 for that one, for the final. And see, so these numbers here, you know what they're called? They're called coefficients. These numbers here are called the coefficients of the polynomial. Okay? And there's a coefficient for that one. Now again, please remember, this is a nice quick way to do this, but if you forget that 0, you'll get the wrong answer. Okay? So one little thing you have to watch out for when you're doing synthetic substitution is you have to watch out for zeros. Now let me show you this little process. I'm going to demonstrate it, and after you see it a few times, you're going to say, hey, that's pretty quick. You just do. Okay, so what we do is we drop this number down and we write it down straight down right there. 2, bam. Everybody got it so far? This is a sequence of steps. It's repetitive. What you do is you take your number that's out here and multiply it like that. And you get 6, right? And you write that product up here, and then you add. -5 plus 6? 1. Right? And then you take this number and do it again. You multiply it here. 3 times 1 is 3. And you put it up here. And you just keep going down this until you get to the final one. And so you put a 3 here. Alright, 0 plus 3 is 3. Alright, if you think you have it figured out, go ahead and continue. Give me the number that goes here, the number that goes here, the number that goes here, and the number that goes here.
9, 5, 15.
And please tell me that number there is 23.
You told me to tell you.
Keep doing the chain and see what you get.
Got it.
Is that what you got?
Yeah, that's what I got. Man, this is so much easier.
Now, isn't it cool?
That is great.
I mean, so I've seen people be really fast at this, and they can do it like in 5 seconds or so. All it is quick multiplication and addition, adding and subtracting, and you keep going down the chain. And then you have your 23. That's beautiful. That's way faster than what we did on that previous one, right? And trust me, we're going to use this idea multiple times. So let me continue the chain and make sure you guys got the same answer I did. Now, by the way, you don't want to go so fast that you're making dumb mistakes. You make a bunch of dumb mistakes. Ugh. Okay. So 3 times 3 is 9. You put the 9 here. 9 minus 4 is 5. 3 times 5 is 15. Put the 15 here. And 15 plus 8 is 23. Isn't that cool? So where are some pitfalls to watch out for? The 0. My friends, that's where one mistake people do. They forget to put the 0 in. Again, if there's any missing terms in your polynomial, you got to put in a 0 when you're doing synthetic, when you're evaluating using this synthetic substitution. Okay, so that's pretty easy. Please make sure you become an expert at this type of stuff. You want to do this often. Okay, so So we did that one. Let's try another one. Now, huh? What? All right. Do me a favor. Let's try this here. I'm gonna use a different colored pen. Okay, let's use my black. Well, how about my cool purple? Let's try number 16. So, again, what you do, I'm going to just move this a little bit. What we do if we're going to do number 16, we make the little box thingy, put the -2 right here, and then you put all these coefficients. Now, by the way, are there any missing in this one?
Oh, no.
There's none missing, so this time we don't need a 0. So we put an 8, a 12, a 6.
So we have the option to do direct.
No, you follow the directions. They'll say do direct, and they say that, you do it that way. Because you got to know both. On the day of the test, and then you have a +9 here, right? +9. Oh, you don't really need the positive there. Okay, but then what you do is you just give yourself some room to do some addition and subtraction. So draw a line across about this length here. And then you start the process. You just do this little zigzag. You zigzag through here until you get the final answer. Okay, so you drop the 8 down, straight down, 8. And you multiply these two. -16. And you add these two. Hopefully you can do this quickly. -4, right? Negative times a negative is a positive, though. So this is +8. 6 plus 8, 14. -2 times 14 is -28. Okay? 28 and 5, -33. Is that right? And then negative times a negative is a positive. So this is +66. And 66 plus 9, 75. Now, is that really true? Is it that fast? Now let's say you're going to do this the direct substitution. You'd have to plug that in right here. Plug the x in right here. Plug the x in right here. Could this really work? I mean, someone discovered this. Isn't that nice? So let's do 8. I'll just do it real quick because I'm pretty quick at this. We're going to do -2 to the 4th power plus 12 times -2 cubed plus 6 times -2 squared minus 5 times -2, and then finally plus 9. Hopefully everyone can see that. Well, 2 to the 4th power is, you got a bunch of negatives multiplied in there, but there's an even number, so it's going to be 8 times 16. Then you're going to have plus 12 times a -8. And then you're going to have, let's see, 2 squared is 4. And 4 times 6 is 24. So I'm going to have a 24 there. And then a negative times a negative is a positive, so I say that's plus 10. And then plus 9. And now, if I do this, 8 times 16, I get 128. 128 for this one. I get minus, let's see, 8 times 12 is 96, I think. 96. And then plus 24, and then plus 10, and then plus 9. And so now if I do this, minus 96 plus 24 plus 10 plus 9, sure enough, I get equals.
Teachers, please release 9th and 10th graders for retake. Have them report to the library at this time.
Oh, bummer.
9th and 10th graders,
Same.
retake. Please report to the library for retake. Thank you.
How about if we do one more before we get started, okay? I want you to do this one on your own real quick. Somewhere on your study guide on the back, maybe. See if you can do that one. Don't forget, there's some zeros on this one. There's some zeros. There may even be more than one. This is a pretty easy method, but if you overlook the zeros, it's going to be wrong.
Don't overlook the
Okay, so while you're doing that, I will also do it for my Camtasia viewers on YouTube.
How many subscribers do you have now?
Oh, hundreds. Okay, I think there's a cube. Okay, so there's a, by the way, what's the coefficient on this one? It's a 1. Okay, so that one's a 1. There's a cube term in there. There's a squared term missing. So there's 2 zeros in here. And then you need to have a 3 and then a minus 20. Okay. So we start the zigzag process. 1, 4, 4, 16, 16, 64, 67. Now every once in a while I do a calculator. 67 times 4, 268. Knock off 20, 248. That's pretty fast, right?
Yeah, that's right.
Anyone else get that?
Yep.
If I've made a mistake, please tell me. Alright, but where's going to be the most common mistake?
The zeros.
The zeros. People forget to put the zeros in. Absent-minded. Okay, so let's continue. So there's another type of thing that will help us graph polynomials. Please understand, here's what happens when you have a polynomial. There's a portion of turns that happens. After those turns happen, the curve does not return. It goes on forever. Like, let's say after you do these 3 turns, this thing starts going on down forever, never coming back. Does that make sense? We would say it's never coming back. And this happens with polynomials. At some point, you get to what we call the end behavior, and the curve never comes back. Same like on this side, it's not going to make any more turns. It's going on down forever. So it never comes back. Okay? And this is what we mean by end behavior. We say it's going down to where? Negative infinity. And this side, what we'd say, it's going down to negative infinity. Does that make sense? I mean, it goes on and on and on. Now, please pay attention, because what we're going to say is a couple scenarios. If the graph goes down, we say it goes to negative infinity. If, on the other hand, the graph goes up, we'd say it's going up to what? Positive infinity. Does that make sense? Now, this side, on the other hand, is going down where? To negative infinity. So you're going to have some graphs that go down forever, and there's no point in plotting any more points, because let's say I create a table of values like this, and I take x's and y's like this, and let's say our standard values that we'll try are like -3, -2, -1, 0, 1, 2, and 3. These are like our standard values that we always try. And once we plot all these points here, usually by then we know what's happening with the curve. And from that point on, there's no point in plotting anymore because we have what we call end behavior. Once this thing does all of its little bitty turns, the thing is either going up or down forever at that point. So there's no point in plotting any more points. Does that make sense? And so the end behavior is important. And so we have a little table in your book. Now please, 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 as you do your first 4 or 5 graphs, study this table. The more familiar you are with this, the better it'll help you figure out your graphs. So, please understand there's some key values on this table. It's also in your book. But there's some key things it tells you here. If the degree is odd, if the leading coefficient is positive, we've done some of this already. You guys remember what happened when we had quadratics? We had y is equal to like 2x squared minus 5x plus 6. What did you guys say about this? Does this open up or down? It opens up, right? Because of that, right? That first term is called the leading coefficient. Does that make sense? Please pay attention. This will be a lot easier if you pay attention here. That's what they're talking about here. The leading coefficient is the one with the highest degree. It's that number that's out in front. Okay, we knew from parabolas that this meant that the parabola opens up. Well, if the parabola opens up, then what's the end behavior on both of these? They're going to positive infinity, right? You see? If the parabola opens up, your end behavior on both sides is positive infinity. And that's what they're saying here. If you have, now by the way, what's the degree on this? This is even, right? So do we have degree odd on this one? No. The scenario that we're looking at for parabolas is like this one. It's an even one, so both sides either both go up or both sides go down. Does that make sense? And that happens on degree even. If you have an even polynomial, the end behavior will be either both up or both down. Now on the odd ones, one of the sides will go up and one of the sides will go down. So this one goes to positive infinity, this one goes negative. Or it might be this way. Positive infinity on this side, negative. It depends on what the leading coefficient is. So there's 2 things that you need to look at to determine the end behavior. The degree and the leading coefficient. So please, my friends, become very handy at looking at this. This will help you figure out what's happening with the graph as you move along the x-axis. What happens as you go out this way? Is the curve going to go up or is it going to go down? What happens as you move along this way? Is the curve going to go up or is it going to go down? That's what we call the end behavior. And since that's the end behavior, there's no point in plotting any more points because you've taken care of all the turns, and from that point on it's going to keep going. It's never coming back. Does that make sense?
So the way that graph is made, is you have to plot the points that you get off.
You start plotting points, and then you study this to understand how the end behavior goes. Let's try a problem real quick. You have your study guide, right? I'm going to do one right here, and you can compare it with your study guide. You're going to do some of these on your study guide as well. So what do we have to do? Well, to graph these, we're going to have to do lots of work. And these problems are annoying because they take probably in the beginning about 10 minutes each problem. And that's annoying. So, so first things first. What you're going to want to do is this on all problems. And now what I would recommend, you're going to put an X here, you're going to put Y here. We have standard values that we'll always use, okay? Let's just be in the habit of doing this. -2, -1, 0, 1, and 2. Now, I will leave it to your judgment whether you should put negative 3 in here or not. And positive 3. Okay? This can take a while. Now, I'll tell you the easiest one to do. On some of these, I'm going to use direct substitution. This one. 0 is the easiest number to plug in. Because that's 0, that's 0, that's 0. So that value is negative 3. You see? That one's easy. Now, to be quite honest, 1 is also easy to do. So I'll tell you what, with 1, I'm not going to do synthetic division. I'm just going to plug the 1 in myself and do this one in my head. Can't watch what I mean. If I plug in 1 here, can't I cube 1? What's 1 cubed? It's just 1, right? So that's going to become negative 1. Can I put 1 in here and square it? That's going to be 1. What's 3 times 1? 3. And what's minus 3? You see, so 1 is another easy one that's really easy. 3 minus 3 is 0, and 1 minus 1 is 0. Okay, so this one's 0. Now, by the way, can you put 0 here? No. There's no symmetry. Usually there's not symmetry. Can't say forever, but most of the problems you will likely not have symmetry. Now, negative 1, I would admit, I would just plug them in again. I mean, I would just do the direct substitution. Does that make sense? So negative 1, I'm thinking, okay, this is negative, but if I cube negative 1, okay, if I cube that one, I'm going to get negative here. Negative 1 times negative 1 times negative 1 is a negative 1. And when I multiply it by that extra negative 1 there, then it becomes a positive 1. And then here, if I do negative 1 and I square it, a negative times a negative is a positive 1, so I get a plus 1. And if I put in a negative 1 here, I get 3 times a negative 1, which gives me a negative 3. And then I have another negative 3. So negative 3 is negative 6, plus 2, that's negative 4. So that one was pretty easy to plug in just directly. But I'll tell you what, after a while I'll probably just do synthetic substitution. Like this one. I'm plugging in a 2 here, I'd do negative 2. And I'd do negative 1, 1, 3, negative 3. And I'd just do it this way. Negative 1 here, negative times negative is a positive, that's a 2. Right? 2 plus 1 is 3. Negative 6. Right? So I put negative 6 here. And I get negative 3. Negative times the negative is a positive 6. So that one's 3. And now I come over here and put a 3. Can you see why this takes a little while? Yeah, you can. Don't give me that. Alright, well now what do? Well, let's do one more of these. I need to find out this one, right? So I'm going to put a 2 here. I'm going to do negative 1, 1, 3, negative 3. And once again, I'm going to drop the negative 1. I get negative 2 here, and then negative 1. And negative 2 times oh, that's a positive 2. So that's a negative 2 here, that's a positive 1. And then 2 times 1 is 2. That's negative 1. Okay, so here I have negative 1. Alright, now that you've done that, okay, by the way, you need to show all your work. You need to show all your work on all these problems. Don't come to me and say, oh, I did all that in my head. Okay, I'd like to see your work. Well, now what we need to do is plot all these points on a number line. 1, 2, 3, 4, 5. 1, 2, 3, 4. No, 1, 2, 3, 4. And so let's take a look and see what our curve is doing. It uses my cool purple color. At negative 2, we should be at positive 3. At negative 1, we're at negative 4. Clear down to here. At 0, we're at negative 3. Obviously this thing is turned around. At 1, we're at 0. At 2, we're at negative 1. So what do you got? Now these things, polynomials, keep in mind that all polynomials, these are little curved things, and then they have end behavior, right? They you know, so here's what I think the curve does. It does this, comes down here, turns around, goes back up, turns back around, and does that. I think that's what's happening. Now, there's one thing we could check. There might be some more turns. How do I know if there's more turns or not?
3.
Now that's where that end behavior comes in. Okay? The end behavior. Okay, so there's two things I need to look at on that end behavior, right? Two things. Number one, I'm going to look at the end behavior now. End behavior chart. If you have your book, go ahead and open up to it. It's in your book.
Teachers, if you have any juniors and seniors that need to take retakes for ID, please have them report to the library at this time. Any juniors and seniors who need retakes, please send them to the library at this time. Thank you.
Okay, so there's two things we need. Two things we need for that there. We need the degree is odd. Okay, does that make sense? You guys sure you're on the list? It's not just all. They should have.
I have to take
Okay, good. I just don't want you guys leaving. It's not all seniors, just retake people. All right, now what's the leading coefficient? Leading coefficient.
-1.
It's -1. So the leading coefficient is -1. Now, so with these two pieces of information, hopefully the end behavior is indicated on our graph. It looks like to me that this thing's probably going down to negative infinity, and this side is maybe going to negative infinity also. However, I may have made a mistake here. So now what we want to do is go back and look at that chart. So I'm going to go back now, and let's go back and look at that chart. What was the end behavior? Okay, I had an odd function, right? And I had degree was odd, and it had a negative. You see, I had a mistake. This side was correct. It was going down, but there has to be one more turn, doesn't there? Do you see that? My graph, remember I started up here and it came down like this, and then it came up back up to -1, and it came back down this way. That's what my graph was doing. This was a mistake. It does not go down. The end behavior tells me it's got to turn around and go back up this way.
But how do you know it's odd?
The degree was 3, wasn't it?
Oh.
Isn't 3 an odd number?
Yeah.
So, and wasn't the first one negative? Do you see now how this is going to help you graph your functions correctly? What I should probably do then is I should add in a -3 and find out where that stupid thing turns around. Does that sort of make sense? Alright, I think what you're going to realize is that these problems take a while. And what I want you to do is work on your first 3, your study guide. There's only 3 problems on there. And the last 2 problems are going to take a while. You want to come up with graphs of them. And so let's do that for tonight. And then, like I said, tomorrow we'll spend a lot more time working the full period on this assignment. It's going to take a while. Okay? Alright, so I'm going to end the recording now.